Hey there. Well, thanks as we're live. We've got a clap. That was a quality clap, I claim. All right. Hey guys, what's going on? Memes here. Yes, we're back at the science thing. We've finished breaking the multiverse for the current time being, at least this week. And we're gonna get back to some science stuff. So we're gonna pick up where we left off. We had kind of gone over some bunch of crazy calculations, I claim. Um, that may be able to pinpoint some potential boundaries, but what we colloquially call universe. Um, I enjoy that's term realm of persistence. Why? Because that seems to be where we live. Because if we're going to claim there happens to be a potential limit, then that raises the next philosophical question: is what's beyond there? I claim there would be dragons. I don't know. Uh, because it's we only have particular computations that we can do or at least be able to prove within the system in which we exist, citing Gödel incompleteness, yada yada, all that jazz. Okay, so there is some stuff behind me right now. We have taken pictures of this stuff. Actually, hold on, I'm unsure if we let me just double and triple check before I attempt to erase any knowledge, because we all know that is technically impossible depending on one's interpretation of what the heck a black hole may or may not be. Okay, so we've got that done there. We'll plug this back in. So as we're letting folks stroll in here from the X's, the Twitters, the blue skies, wherever from on the internet you may venture in from, yonder temporally in the future. I don't even think yonder is usually a place associated. Uh, okay, and strike that. Create whatever adjective or adverb that we need there. But what we're going to be going over today is we're going to take what we had there and we're going to lay out generally within the it's very interesting because a lot of things seem to line up within the realm of our current observations, our current measurements, and the general standard concordance model of cosmology. There's going to be a few little twists. Well, there's one really particular, really small little twist that may lead to fluctuations that may imprint bigger twists upon our cosmological observations. And we're going to be laying this out in perhaps a more easy to digest form. We will go through some of the calculations, and again, they're in the previous video from not yesterday, but the day before. I can add them to this one too. Uh, what we're going to do is we're going to commit some total blasphemy. Why? Because within the description that I listed of this video, we listed, can we get something from nothing? Now, it's a very interesting question. I can't. I can't. Uh, you could go into Wolfram Alpha and do one over no thing. If you do that, you will return a complex infinity. Uh, so I don't know if that's something or all things, everything, a complex infinite amount of things. I mean, that just comes up when you divide by zero. There seem to be issues, but those seem to be issues that we currently have within some of the standard model of physics. Um, actually, okay, we do have some infinities, but also I think it's primarily within general relativity, our standard or our model of gravity. It's, as we all know, Newton came along. He gave us 7 digits of precision. And Professor Einstein came along and he gave us 7 more. So we have 14 digits of precision. A good place to play the Professor Roger Penrose Club. Actually, we'll do that right now. We got some friends joining us. Let's see what we got. Hey, Dave. Dave's saying hi to everybody. Yeah, and we got Jax here. Hey, Jax, I can neither confirm nor deny that, but I may resemble that. Well, whilst we're all here, one of the claims that is proposed here is okay. A lot of times it's like, all right, well, we need infinite precision, we need infinite this, we need infinite that. I don't know about you, I can't count to infinity. It's a very big number. Um, I can count to 14 though, because the interesting thing is number one, most of the standard model calculations, basically, if you go into CoData, most of the different measurements for the different stuff and things that we're measuring within certain dimensions or lack thereof, aka their relationships with each other, a lot of those hold really strong for about seven significant digits. After the seventh digit, they start to get a little wonky. Coincidentally, the Ampere constant is proposed to be at precisely 10 to the negative 7. Our, our calculations, it's a little bit different. It's right there, but just off. It's like, I don't know, but like 0.999999299. Yes. Sometimes you got to measure, remember 9 or 10 significant digits for maximum effectiveness, or at least if you want to, if you're going to take the model seriously and be like, all right, there's something to this. If we were going to assume the stuff coming out of our mouths and our conjectures are true, you have to play it out. You can't just be like, well, I don't like this. It's easier if it's precisely 7. Okay, if it's precisely 7, maybe it is. But then again, we may not get a as beautiful, I would claim, um, closed form for the mass of the electron, which essentially, at least for the poster that Thad's getting ready to publish, I think tomorrow, with the updated poster, um, you're going to see some very pretty things. And again, I am very biased. I'm technically a physics monk. That is technically my job right now, to do scientific stuff and things. As Professor Keating has brought up a number of times before, if you're going to attempt to do science stuff, well, you want people to understand what you're saying. Because all the respect to the friends at the IAS, the ICTS, and everything, I'll watch some really brilliant folks, far smarter than me. They'll go up to the board and they'll be, all right, we have our, big L Lagrange, and we've got this here, we have this operator, and they'll fill up like 9 different boards because they'll have like 3 chalkboards, and then they each go up by multiple levels. And I'm sitting there, and don't get me wrong, I've literally gone through and been like, I recognize this. Let me do a calculation. That's fascinating. I didn't know that. So I learned plenty of stuff, but I think your average Sally, Dick, or Jane that's like, I got some interest in this stuff. I just never really pursued it. I would like to make some contact with reality. It's like, listen, you can put it, your standard GR, if you got like 10 by 10 matrices and stuff, it's like, okay, you spend the time, you fill all this out. You should be able to model the different curvature and stretching and warping of space time itself. And it does seem to work really well. It's a lot of work. Don't think there's statistically a lot of folks in general that can do that. I know there are a lot of folks that do that, but of like 8 or 9 billion people in the world, thousands, thousands, tens of thousands, maybe a few 100,000, possibly. Um, I don't know. That's why folks like Jonathan Gerard have been developing um, software like a Gravitas and everything. So it's like, all right, you put in the generalized parameters. You don't need to do all the exact notation, and you're going to get a pretty dang good model about what might actually work. Okay. So what we're going to get into is, let me see. If Dan is, you know what, here, let's do this. We're going to do a quick side segment for Dan. So when he gets here, remind me, because he asked something about a lemnis gate and dark energy and stuff. Going to be a little preview of another little shorter video Thad did, a quick little 15-minute one about, as we can see, this is position this better for anyone actually they'd like to take a look. This is about geometric means. This is Gauss's, that's arithmetic geometric mean. Hold on. Get a little closer. Okay, that makes it a little better. Okay, I think it does. All right. So what the heck is this? Gauss, long story short, he's like 22 years old at the time, and he realized a very interesting thing. You know the whole a squared plus b squared equals c squared. We got our Pythagorean theorem. Shout out to Casey. He's stressed how that explains probably most things. But you can do your standard arithmetic mean. What's that mean? You take some things. Now the smallest mean you could do is you need at least 2 things. So it's going to be, you got your A plus your B. You get your two numbers, you just add them together, and you divide it by the number of numbers. In this case, it's two. So technically, the arithmetic mean basis is one. Okay. You get your geometric mean. What do you got? You got your A times B. And depending on the number of elements, you're going to take it to that root. Since you only got two, well, you take the square root. Well, you raise it to 1/2. Oh, look, we have a little symmetry going on here. All right, so that means our factor is base factor for standard two elements is root 2. Fascinating. Okay. So, long story short, you've got these means, and then if you take the series, so basically, if you do your standard, you get your A plus 1, you get your B of whatever it is plus 1. And if you do the structure here, you take 1/2 of the arithmetic mean. And then if you take the square root of the geometric means, yes, we get those things again. The interesting thing is you take the limit of A, your limit or your infinity, whatever your limit is, and you see if it converges at something. So the limit of A sub n, the limit of B sub n is 2 pi over the arc length of a lemniscate, aka the entire distance around the figure eight. Okay. Why? Why are we dividing literally a circle by a figure eight? The world may never know. Technically, a figure eight with a Mobius twist going to it. Yeah, that's one of the things Dan brought up because he was highlighting the was it Quantum Magazine's recent like outstanding like achievements in like physics and chemistry, and apparently they finally confirmed supersolids. Uh, what's a supersolid? It's like a superfluid, except it's in a solid form, whatever that means. Basically, the the identifier that they had in the video was basically it needs to show some quantum vortices. What is this? Little whirlwinding tornadoes of super stuff or stuff that allows us to do super things, aka you have your standard bucket of water and you do your Newton bucket experiment. You got your bucket of water, you put it onto a rope, you wind it all the way up, and you let it start spinning and spinning and spinning and spinning. What happens? The water goes up the side. Why? Gravity and everything. Duh. Okay. Apparently, when you do that with a superfluid, such as now I'm not sure if this is just a characteristic because I think it's superfluid helium 3 because helium by itself is normally lighter than air, but if you're going to do helium 3, that would assume that it would have more protons, right? I believe, or is that left? Okay, irregardless, that's a Bostonian term. It means regardless. But basically, if you do that for a superfluid, you start spinning the bucket. The bucket's just going to go around because it's a superfluid, so it doesn't really need to respond like that. However, if you take it to a critical point, you're spinning fast enough, it's going to build up some form of angular momentum around it. That once it reaches that critical point, you're going to see little vortices start to break apart. And little vortices, not just in the center. In the center, yeah, that makes sense. That's a standard Newton bucket thing. But if you see these vortices just kind of appearing around it, it's such a crazy phenomenon that apparently Dick Feynman allegedly said, or at least I heard somebody say that he said that once that phenomenon was observed, he's like, I had a dream about something like that 20 years ago. It was so crazy, I was afraid to tell anyone. Um, I have no idea whether he made that up or not, but I have spoken to other folks that have had very interesting things come to them in dreams that may or may not pan out into some form of reality, whatever that might be. Okay. The short little part about the lemniscate here is you have a unit lemniscate, and apparently one of these limits, I think it's the arithmetic mean is the larger one, the geometric mean is smaller, but you have your unit lemniscate, and it seems to be a quantized lemniscate going through there from inside to the limit of the unit lemniscate, and then it seems to be larger and then quantizing inward to the unit lemniscate. So I was thinking, I'm like, oh, wait a second. How could we do something kind of crazy like that? What if we use building blocks? Because Rick has brought up, what if we use blank time and blank length as building blocks? I'm like, all right, well, Star has said, oh, he believes there's some Octonian internal connection. I'm like, all right, how the heck do I get up to 8 dimensions of stuff? Okay, well, I'm like, if we do c squared, that's the thing. So we could do. I know. I'm getting a little bit more technical. I apologize. But if we just do our standard c squared, blah blah blah, speed of light squared, that's equal to length per unit of time squared. So Planck length is the Planck time. You square that, so that means we get two Planck lengths. You get two Planck times. That gives us 4 dimensions. Wait, aren't we claiming there's some double cover, some hyperbolic figure eight knot or its complement or something, utilizing the volume of two hyperbolic tetrahedras? So if we had a double cover, we had two of those. Could we do something crazy? And I don't know. We're gonna double that. What if we multiplied it by itself? Well, that would turn this into Planck length divided by Planck time to the fourth, which ends up giving us a total of 4 dimensions of length, 4 dimensions of time. That makes this C4. Now, not the standard boomy type when you hook up your different electrodes. No, that's not what we're looking to do here. However, C4 is interesting because, wait a second, isn't that the standard Einstein C4 convention for kappa or something? AKA the Einsteinian kappa? What is it? It's like measure. I think it's the stiffness of space time or something like that. AKA, it's supposed to be really stiff. Hey, upcycle. No, we're just coming into some blasphemy right now. Or excuse me, we're conjecturing up to our actual blasphemy. Uh, we're just talking about figure eights, lemniscates. Oh, right now I'm just kind of thinking out loud a little bit about what what you could do. So I'm like, all right, well, this will give you 4 dimensions of this, 4 dimensions of that, 4 dimensions of length, 4 dimensions of time. Gives a speed to the fourth. All right, if you got a double cover there, and if you got a lemniscate, you got something kind of doing the figure eight thing. It's still on the figure eight, but it's also under a Mobius twist. It's also swishing back and forth and rotating in there. I'm like, well, if we had the Clifford torus, which I did have a thing on this channel. If you type in Clifford Taurus, you're gonna find a picture of Clifford the big red dog with next to a big donut like Clifford Taurus. What's the Clifford Taurus? Apparently, according to the Nash embedding theorem, which I troll a lot of folks here. It's mostly good natured, but we want to have some fun. Just help people remember things. Yes, I used a picture of Kevin Nash in the Nash embedding theorem. Uh, but basically, what it is, it's this little thing. It's really small, but then as it's rotating, it's really, really big. So I'm like, if you have this dang stretchy donut just literally going around the Planck frequency, constantly updating, constantly updating, constantly updating, I'm like, all right, I'm glad I can't see at those magnitudes because I would probably get really motion sick. Um, that's rampant speculation there. That's not the speculation you're here for, though. No, the speculation that we're here for today is we're going to commit some blasphemy. Why? Because we're going to at least conjecture about some cosmogenesis. How the heck did we get here? What the heck is going on? How may we explain our observed phenomenon? I'm not sure if that actually really rhymed, but it sounded really good coming out of my mouth. Okay, so as we go over pacifiers slash orbitals as we're erasing these things, um, yeah, hopefully everyone is doing well. Hopefully everyone is making the best they can and not having any and intentional or negative drone incursions or anything recently. Because listen, all I know is I watched the movie like the rest of you. They told us don't look up. Everyone starts looking up and people start losing their minds. You're watching, you're watching. the professional local. Listen, some random person on Twitter is like, "Oh my God, there's an orb in the sky." Okay, it's a random person on Twitter. They can totally say that. When you have your local ABC affiliate pointing their professional camera up in the sky, being like, "We've never seen anything like this before." It's all of a sudden where pretty much every astronomer, professional and amateur, is then like, "You've never seen Venus?" The best part about it is it's like literally we're one step away from there's an unexplained phenomena here. How do we explain it? There was a swamp gas pocket that got caught that reflected off of Venus. We're literally to the Men in Black level with no, 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 no. What you actually saw was like some temperature gradient magnified by the camera and the atmosphere and everything, and Venus, which happens to be Venus season or something. Uh it's and unfortunately that's what you need to know. It. Hey, I don't. It looked really weird to me. I've never seen anything like that before. But before I go, I'm like, well, obviously therefore aliens. Maybe it is. Maybe it is. You try to look for the easiest scenarios that there might be. Yes. Phenomena. That basically is where we're at now. Okay. So where are we at? All right, let me slightly caffeinate and then we can continue with our blasphemy. Mm. A lukewarm hazelnut to get the old noggin a jog. All right, it's up in our camera a little bit. Okay, so as I see it, there might be about maybe 3 plus 1 possible scenarios. Number one, God. Okay. Number two, perhaps we were created as some form of an experiment. Perhaps, I believe, as Professor Avi Loeb, he conjectures the scientist in the white lab coat. Perhaps we're some, I don't know, kid's science project in some higher dimension or something. Possibly. That then beggars that beggars the question. It's like, what's the difference between number one and number two? I don't know, belief structure, something like that. Okay. Number three, well, at that point, you're getting to um you might need to invoke well the standard way we do it is we one you watch you listen to folks and they say cosmic fluctuations. You literally have hand waving built in. So I take that as just some wizardry. Some hand waving wizardry, aka we don't know, we're not sure. And I don't know, you're casting a spell, let there be light, something like that. Possibly, possibly. We'll get into how that I could try to conceptualize that. Now, basically, I can't get something from nothing. I've heard that conjecture. What happens if you had a just void of randomness, just randomness, and then all of a sudden you have some wave patterns come together, and then once it has its smallest geometric form of persistence, aka the hyperbolic figure eight knot, which is basically just get your little figure eight over here. You can represent it like that. Hold on, let me make it a little bit more balanced because I can be a wee bit anal. Okay, got our little figure eight over there. Okay, but technically it's actually toroidal. I'm gonna bounce back in on it. So okay. Ooh, look, it's Deadpool again. Yeah, of course, Deadpool is the center of the universe. Some people may agree with that statement, but that's our side. Okay, so if you had some form of persistence, or I think it's maybe it's just a hip thing to do, or maybe I'm just more of a Wolfram fanboy. You invoke the Roliad. What is the Roliad? The infinite potential of all potential rules. So I'm like, well, that sounds like a lot of maybe an infinite dimension at Hilbert space. If you just had the a realm where anything and everything will eventually happen. At some point, you're going to have, I believe, as Professor Barron does from Harvard says, you're going to have a configuration space. So this board essentially is our configuration space. Why? Because it'd be roots are right on the walls. We still live in a society, at least George Costanza would claim. Uh, but okay, let's say at this point, just randomness or rules of the ruliad aside, you get some minimal balance for. Okay. So then whatever else is over here, once you have something that persists, maybe it's going to have a little bit of gravitas. Why? Because it's persisting. And then, as Jen shouts, Jen from the Church of Entropy, all of a sudden, whatever other waviness or rules and stuff within its vicinity just all start to come crashing down, kind of like the intro to the Hulk Hogan theme song, or by Rick Derringer. When it comes crashing down and it hearts inside. Dun, 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 dun. Something like that. Okay, so if you get everything twisting and crashing down, might that be enough force to, I don't know, maybe invert this dang thing? But instead of a cosmic hernia, it leads to the cosmogenesis that we observe, I claim. Okay. Because it's a conjecture. It's a conjecture. And we'll see what happens. So, what does that end up doing? That would have it end up projecting out to too many pockets. All right. So, a hyposphere of maximal volume, we're going to claim. So, at least according to the calculations that we've done, it looks like it is a four-dimensional hypersphere that apparently, according to a lot of smart people that are not myself, we can use a four-dimensional hypersphere, perhaps quaternions, or maybe even as low as the pseudo-quaternions, which I believe utilize three elements. We can use that. A little skinny on that side. We want some more curvature. But basically, we'd have enough to compute the stuff and things that go on, or at least have it be coherent that we can try to figure it out as best we can. Okay. I'm not saying there might not be an infinite level of recursion. Perhaps it is turtles all the way down. Turtles, hyperrulal turtles, whatever the heck you want to call it. Okay. I cannot say. I can only exist on about a meterish magnitude. Okay. So what could we claim here? All right, we're gonna claim this is small. Let's actually label the structure with something a little different than what we're doing with. Okay, this should be good. So this right here, I'm gonna say it's very small, or about 10 to the -8 meters. Okay. Now this is important because if we were to have something like this, if you got this little vortex, you might say, going along, sucking things in, putting things out, if we start from a much hotter, dense state, and you had a field configuration where this was here, and again, this just kind of happens to be a happy consequence because Assad was going through a lot of computations. He kept finding like he's like, volume of a hyperbolic figure eight, not volume of the Gieske manifold. He's like, WTF, mate, what is this stuff? You start to look at it and you're like, wait a second. The hyperbolic figure eight knot is actually the first knot with a knot theory that projects a hyperbolic manifold. The hyperbolic figure eight knots, its complement, actually. So basically, everywhere where the knot is, or excuse me, everywhere where the knot is not, is where the complement is. There we go. I think that's the sentence. So everywhere the knot's not. But basically, if you use a toroidal boundary that happens to be a double cover of the minimum balanced three manifold. It has a total of 10 Dane surgeries. That's the most of any other knot there. It's very suggestive of potential base 10, but that's not what we're speculating on. We have enough blasphemy to conjecture here. But it's also balanced, and it's also literally like I believe, as Professor Segerman that said, oh, it's kind of like having your worm eat its way through an apple. I'm like, oh, wait, so its vortex throat is kind of like a wormhole. Not like anyone's ever predicted something like that. Now, it might be a very short wormhole and everything, and perhaps you could traverse it. I mean, you probably don't want to because you're probably going to be torn to elementary sheds because the vortex throat's only about 10 to the minus 18 meters. Coincidentally, about the charge radius of a proton or neutron. It's the old noggin a jogging. But okay, so let's start off with what did we have the other day? We had, let me just grab my notebook and we'll put the other stuff up there so I don't get it completely wrong. Okay, so we had okay, I thought this was pretty cool. So actually, let's label this. We'll say that this is this one. So we'll call this a four-dimensional hypersphere. All right. So four-dimensional hypersphere. Okay, just in case if anyone asks. Yeah, I can spell sometimes. Okay. Oh, and we're going to claim that the radius of this is 10 to the 34 meters. So it's a red pen in some pocket. Oh, that's green. Already got like four markers in my pockets. Oh, it's a fun day. All right, that's about 10 to the not minus 34 meters. 4 meters. Okay. So, okay. But we started from a hot dense state. Let's start our blasphemy here. Okay. So, coincidentally, if you do the relationship that we had, that if we were to conjecture, and the claim is that if you take mass of the universe, so m universe divided by the Planck mass, so m sub p thing is equivalent to meters over the Planck length, L sub p, and we square this. Okay. And the thing that really caught me about that is originally it's like when you have folks like Dr. Salvador Pius and I know Rick DeWitt did give a presentation here where they were basically saying the same thing about utilizing the Planck force as some form of a constant. So basically what we were doing is we were taking the Planck force and then what is it? We did F sub p, so it was force Planck is equal to is it mass of the universe, so m universe times c squared, b squared over radius, r universe. Yes, because it's our universe, baby. Arg. I think it's a pirate day. Okay. And the fantastical thing is when you did this, you got a number out. That number out happens to be 8.331 times 10 to the 61 kilograms. All right. And once you have that number, you start playing around. It's like, all right, well, just because the standard mass of the observable universe times c squared divided by the radius of the observable universe gets us to about the Planck force, or the Planck force, like with an 8 pi factor or something in there. Um, but the interesting thing was when you do this, you're like, okay, you get the number that way. But if you set it up like this, meters over the Planck length squared, you throw on the Planck mass. If you just put X kilograms in there, you amazingly get the same number. 8.331 331 times 10 to the 61 kilograms. WTF, mate? What's going on? I really got the old dog in the jog. And again, I like to thank Rick. I mean, he kind of gone through this in different ways. But all I know is I asked Rick, I'm like, I keep getting this calculation. It was like 1.45 or something times 10 to the minus 18 for acceleration. I don't know what it means. And I just see the look on Rick's face. And again, I got love for Rick. He has the worst poker face in the world. And that at the time, it looked like he just wanted to turn around. We're at like the Seaport District up in Seattle, Washington. I felt like he just wanted to like go over to the railing and just scream at the top of his lungs the answer. He did not. Well played, sir. But they just basically just gave you his responses. Oh, there's something very interesting here. I come back, write it up in another way, and then Thad just does the magical Thad things like, oh, you got to rewrite it this, and I'm like, huh. I mean, that's very pretty. It's it also seems to line it up with Professor Sean Carroll's biggest ideas in the universe. At one point, when he was describing physics, he's like, "In physics, we do calculations. We use different mathematics. You get an answer that doesn't make sense. You square it. You see what happens, and that's all we really did there." And again, we're basically just using algebra here. It's like, okay, we're using stuff that, like, at least initially, I kind of, oh, you gotta solve for x. And they'll teach you, it's like, well, you do all this, yeah, 4x, blah, blah. I don't even remember the whole thing there. Plus or minus, you need to take the square root. So it's got a positive answer and negative answer. And you're sitting there, you're like, when am I ever going to use this? It only took about like 30, 25, 30 years. And be like, oh, I see a reason for learning this stuff now. Why didn't anybody say anything cool like this back then? I was terrified of math for years, but it's okay. So, okay, so we got these things. So it's like, all right, we're gonna claim this is mass of the universe. And it's probably spread out there. I'm like, wait a second. Why would we do that? Okay. We still haven't got to the beginning yet. I apologize. We've been going on for 37 minutes and we haven't even gotten to it. So that's about in line with our standard broadcast here. Okay. So what are we going to do with these numbers here? Okay. So the standard concordance model of cosmology and stuff, it's like we start from a very hot, dense state. Okay. Now, a lot of times you'll hear things when you spend time on the science YouTubes, you'll hear the Planck length, the Planck mass, the Planck time, occasionally the Planck temperature and stuff. Um, there are other Planckian values, which basically just means our standard dimensional units, like c is speed. Why? It's length divided by time. Got a unit of length per unit of time. All right, there you go. But aside from that, there are some other ones. And the one we're going to talk about right now is the Planck density. What is the Planck density? The Planck density is like, I think it's like 5.96 times 10 to the 96 kilograms per cubic meter or so. Ginormous number, 10 to the 96 magnitude. Okay. So coincidentally, if we take our conjectured mass of the universe, so we do M, universe. God, so much blasphemy here. I mean, again, we're just lining up units, finding interesting things that might be plausible, or exploring a hypothesis. So we'll see if it holds up. So if we take the mass of the universe, the claim we have there, and we divide it by the Planck density, we get a very interesting number, which increases my Bayesian priors, my credence, so to speak, and that maybe there's a little bit more there. Because what we get is one Planck length. We get the Planck length times meters squared, aka is it 10 to the minus 30? Hold on, I know at least the first three digits. The Planck length, you use it so many dang times. All right, 1.61 times 10 to the minus 35 meters cubed. Wait a second. Wait a second. I'm kidding. If we take the conjectured mass of the universe that we're, and again, hey, maybe you think this is just pulled out of my butt. Hey, my butt is right here. Feel free to take a look at it. Feel free to take, that sounded very wrong, but feel free to take a look at this. Feel free to trust, but verify. That's the thing. It's like, yeah, most things are wrong. This is probably wrong because most things are. Now, if we assume that once we set units in a coherent system like meters, kilograms, Kelvin, and we keep tuning it to the best of our measurements and observations, that maybe, just maybe, we could learn something useful. I believe it was Vanessa that said, nature is simple. I think I think that's where the whole aesthetic, or at least I forget whether it was The Rock or somebody said it's like, no, 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 no. In order to understand physics or make progress, we need to see beauty within our equations or mathematics or something. And when people say beautiful, you can make any beautiful equation. But then again, if you have to input all these different other parameters and everything, is it still beautiful? Is it clunky? And maybe it works. I think they call that kludging. What is it? You just throw in enough extra stuff to get it to work. I had to do that for some finance homework in college. I stayed up all night solving this problem in the back of the book, and then eventually you get to class at like 9 a.m. in the morning, and all of a sudden the finance professor's like, "Yeah, so that problem didn't actually have an answer in the back of the book." I'm like, "Stayed up all night and created an answer." I did a kludge and added stuff and things to get it to work. That was a little ornery that day. Not a lot of sleep, but I'm like, okay, so is this simple, or at least if you can find some simplicity in things and relationships, especially from things we already know. We believe the Planck length, the Planck mass, and all that jazz are things, and we do use them in our calculations already. Is it really that far of a stretch to think like our base unit of length, the meter, divided by the minimum unit of length, and we square that whole dang thing? Might not be equal to the sum total mass of universe divided by the actual standard Planckian boundary of mass. It's interesting. It also gives us a plausible number. So it's about 8 orders of magnitude. The mass in the observable universe is about 8 orders of magnitude. Um, the radius of the observable universe. And if we want a hot, dense state, let's say we have that cosmic initiation, we wave our hand, perhaps we get some manifold of persistence that whips and all the energy and waves and everything, and it then is starting to invert, but it's not at its current state. Let's just say you took all the mass of the universe and you divided by the Planck density. If you did that, and you happen to get out the Planck length times 1 meter squared, you get about 1.616 times 10 to the minus 35 cubic meters, aka radius of universe at cosmic initiation, uh, is about the Compton wavelength of the electron. Okay. Because if you take the cube root of this, you get that out and you go to about 10 to the minus 12 meters for a radius. So basically, about the size of, let's say, a primordial atom. Where have we heard that claim before? It's amazing how much it actually seems to line up. Now, here's where we commit some serious blasphemy. Okay. So if we're at about the Compton radius of the electron, we about have this volume, and we have this. Now that mass is probably going to be condensed mass. It usually gets pretty hot. Okay. What happens if it gets pretty hot? Well, if you here's a real kicker. So now we take the mass of the universe. It still sounds weird every time I say it. And then we do this thingy up here. Let's get the energy out of it. What would its mass energy equivalent be? You multiply that by c squared, little mass energy conversion, and now we invoke another Planckian unit. We're going to invoke the Planck spring constant. What? It's just the thing that they teach in first year of physics and stuff. I never completed first year of physics, so I'm a little bit behind, but apparently it's a thing. It's basically mass divided by time squared. That's a very interesting thing. So it's like Planck spring constant. Okay. So that's a thing. But when you do this, you get the total mass energy of the universe. So this equals, this is about 10 to the 78 joules. And this ends up being in the Planck spring constant, which is like seconds, was it kilograms divided by seconds squared. That coincidentally ends up also being 10 to the 78. Okay. It's actually 7.44 times 10. 7.44 and times 10 to the 78. These things line up. I'm like, wait, hold on, wait. What you're saying is, at least according to these calculations, again, they could totally be wrong. You take the total estimated mass of the universe, you multiply by c squared to get the mass energy equivalent of universe, and you divide by the Planck spring constant that just happens to be 10 to the 78 of magnitude there, you get out 1 meter squared. Oh, what was that? See. Oh, dirt. I can spell sometimes. But you just look at that, you're like, wait, hold on. The spring constant, isn't that thing where you see all the YouTube videos and they're like, take an idealized spring system. You got a spring, it's on the wall. We take friction out because that's too complicated. We put a little box on the spring and we give it a nudge. And we see how it. I'm like, wait a second, the Planck spring constant is equal to the mass energy of the universe. Oh, that might explain why the Planck spring constant is so ginormous and the Planck density is even more ginormous. I listen, I just see these things that come up and I'm like, I have no idea why the Planck spring constant is 7.44 times 10 to the 78 kilograms per second squared. That doesn't mean anything to me, except I'm like, all right, well, there must be a lot of space itself must be pretty dense or have a particular magnitude, but it just seems to be very interesting that it balances at the magnitude of 1 meter squared given our convention there. So, yeah, listen, hey, these are just the calculations, and I'm just taking our standard concordance model and what we know. People are saying we came from a very hot, dense, compact state. I'm totally willing to believe that. I'm like, all right, that's what most folks think. That's fine. I'm like, can we estimate how much stuff was going on when these different things and epochs were happening? And I'm like, all right, let's do a crazy thing. Like meters, divide by the Planck length, we square that. All right, and then we solve for x kilograms divided by the Planck mass. Boom, you get this number here. You take that number there, I'm like, okay, is there a way to maybe verify that number? Well, seeing as previously on some other episode like a year ago, we take the Planck force equation from Dr. Salvador Pais, and Rick had mentioned it here before. We set that equal to the what is it? We solve for x here, so we would do solve for x kilograms because we have the Planck force is like 10 to the 44 newtons. Uh, have x kilograms times c squared divided by radius of universe. When you do that from our observable universe, you get approximately the Planck force. So, well, if we're going to claim that the radius of universe is about this, which this number here is actually, oh, actually that's it's just meters squared over Planck length. So this is meters squared over LP, because the magnitude, this is just simply the magnitude since we have it squared, that has it come out to be with its correct unit there. So wait a second. We're just dividing stuff by similar stuff, occasionally squaring some of this stuff, and we seem to be getting things that follow logic and maybe reveal more information. Now, very interesting. But hey, Jimmy, what are we doing? Well, part of this, Jimmy, is the claim is we have certain boundaries of dimensions, in that we use the units, or at least within the constants of nature, and this was something that Thad had pointed out to me, is from all the dimensionful constants of nature, and some of them that don't express dimension, you can build them up from five bases: time, space, charge, mass, and temperature. Now, it might be a complicated version of that. Maybe you got Boltzmann's constant, so you got like mass, so you got temperature, maybe like there's like some distance and everything in there. But ultimately, you can decompose them into five bases, kind of like we have five platonic solids in three dimensions. We got six of them in four dimensions. Um, well, that's an interesting thing in and of itself. But okay, so if we get that and we plug something into here, so if we take this unit, we claim that's radius of universe. We take our c squared, we set it equal to that, we solve for x. Oh, look, we get the same number. That's very interesting, maybe a little suggestive. And then finally, it's like I looked at the Planck density once. I'm like, I don't even know how that works. I'm like, this doesn't seem to even make any sense. It's like, I don't know, it seems like great black holes or something like that. I'm like, I don't know, it's 10 to the 96. Well, if you have to take 10 to the 96 and you divide it into that, um, the numbers at least happen to cancel out, because well, that's 10 to the 96. We get that. So we get about 10 to the minus 35 in units of meters, or excuse me, cubic meters, because it's the Planck length times 1 meter squared, which coincidentally is the mass energy equivalent of universe, according to this claim, divided by the Planck spring constant, 7.44 times 10 to the 88 kilograms per second squared is 1 meter squared. And that appears to be that 1 meter squared times the Planck length for these things here. So again, it's very suggestive, but if we're going to believe that we do have coherent units and we have Planck bases that we can construct, perhaps maybe it's the relationship and magnitude between these different things that help us get to where we are. Okay. So if we're at, I don't know, about one Planck length of cubic volume, or about, let's say, we're about 1.6 times 10 to the minus 35 cubic meters. That sounds like a primordial atom. It's right about Compton electron radius there. Okay. So, or Compton wavelength of the electron. But if you have that really small, but it's also probably really dense. So the simplest thing is maybe it expands. Maybe it goes outward. Now, here's where we're going to differ. Now you can I'm not going to get into, oh, what's doing this to that. Let's do the simple thing. Let's assume standard concordance cosmology. We got a primordial, super hot, dense state. And then it starts to expand. Okay. Keep everything how we believe it. I'm not sure we really need inflation. Maybe it's a thing. Uh, could explain a lot of things, but if you had a little, let's say, hyper pump in the center and it's spinning around, if it has some angular momentum as things are going outward, when we normally see cosmic ripples, and if we assumed some level of superfluidity or something, maybe our little quantum vortices from Professor Feynman's dreams started to occur. You started to have mass accumulate and everything, and you could explain, I don't know, seeding of some of the initial galaxies and everything. And if it persists and we cool down to about 2.73 degrees Kelvin, once we get to that state, well, we're probably going to see a lot of galactic formations. And if we're only looking out at, we normally look out about standard cosmology is about 10 to the 26 meters. Okay. So all I know is maybe we're somewhere, I don't know, maybe we're a little speck. And if we can only see out so far, again, not to scale, not to scale. I think that's important. But if we can only see about 10 to the 26 meters, and we got a little bit more ways. It's about 8 orders of magnitude further out. Things are probably going to look flat, not much curvature, not much going on aside from looking back, be like, wow, there sure are some really big galaxies that we did not really account for. Why might that be? Maybe we exist in a very vast sea of space time. An idea, but let's see what else we got. Yes, we eventually have to get to at some point. Uh, yeah, no, perception makes a very big difference, see blue. It's because here's the thing. If you don't even have a concept of what you're looking at, it's like, what are you gonna think? I don't know. If you're chilling on Sentinel Island, those folks haven't really interacted with other folks around the world. You cruise up on a sailboat, are they really even gonna know what that heck that is? It's like if you've never seen something, how do you conceptualize something? It's, and any sufficiently advanced technology is indistinguishable from magic. So when all else fails, just invoke wizardry. You just say a wizard did it. Because maybe it's, I don't know, you pull somebody out of the 17, 1800s and be like, dude, check this out. You pull a little flat tablet from your pocket. It starts emitting light. You're like, dude, are you hungry? And in 25 minutes, you have hot, tasty food appear at your door. That's freaking magic. Because if you don't have any some conceptualization, it's like, what? You didn't go out and murder any chickens or anything. It's like, how do we have hot, tasty chicken? And what are these forbidden spices? Buffalo sauce. But it's one of those things. If you have yet to have the conceptualization of a thing, how would you conceptualize a thing? And that's all it is. Because, all right, let's say we start off, we have a very hot, dense state. All right, we start expanding out, but you got a little rotation in the center there. As that thing's rotation, it's doing its stuff and things. Maybe it's sucking some things up, spitting some things out there. But as you're expanding from, I don't know, about 10 to the minus 12 meters to about 10 to the 34 meters, yeah, that's a lot of orders of magnitude. So that brings us to 12. Okay, so that brings us up to about 46. Oh, no, negative 12, 44. Yeah, no, about 46 orders of magnitude or so, uh, as far as radius goes. And maybe there was inflation. Maybe we got to this point really fast. Hey, maybe we just had standard things until we got up to a balance point there. Maybe we're still expanding to get to 10 to 34 meters. Maybe we're going to cool down to 1 Kelvin. I think it would be very interesting if all of a sudden, once we hit 2.718 degrees Kelvin, if the cosmic microwave background holds steady, because at that point it would literally be base E in Kelvin. See, that's a totally fantastical conjecture right there. Just because we measure it, I'm like, at first, I'm like, it's below that, so it can't be. And then you look at it, it's like, it does seem to be rather uniform. It's about 2.73 degrees Kelvin. And I forgot what E was. I just knew it was 2.7, but it's 2.718 uh, for the base of natural logarithms. I mean, what if we had a standard operating temperature, base E? Maybe that would unlock a lot for reality, but that's all we got for right now. Basically, played around with this, and yeah, hopefully made a little bit more sense. And I occasionally like drawing things. But are we an old game that runs on old hardware? Hey, maybe it's best hardware. Maybe it's being updated. It's a fun thing to think about. But other than that, take care of yourselves. Peace out, everybody, and have a good weekend, y'all.